Hi everybody, welcome back to another video on the Rhythm and Time Toolkit. So today I'm going to talk about pattern objects, which are a family of objects within RTT that generate rhythmic patterns. And the way that they do that is by receiving or generating a list of zeros and ones, basically, storing that list inside of the object, and then allowing that list to be played back. So I'm here starting off on the help file for pattern objects within the package. And the way that you can get to this is either through the package launcher or by going to Extras, Rhythm and Time Toolkit, and then selecting rtt.help.pattern objects, which is right there. That'll open this file, which contains pretty much all of the information that I'm going to give you in this video, but I'm going to just open up a fresh patcher and kind of walk you through. Before I do that, you can see here there are 5 different objects. Like I said, what these have in common is that they either receive or generate a list of zeros and ones, what you might call a gate pattern. And what they also have in common is a shared format for the inlets and the outlets. So all of these kind of work the same way in terms of how you talk to them and the type of data that they output. The differences are just really in how they generate that gate pattern. In the case of rtt.pattern, it just receives a list of zeros and ones that it gives you, and that's it. For the other ones, it uses pretty simple algorithms to generate those gate patterns. I'm not going to go into tons of detail about the specifics of each one of these. You can explore them, check the help patches out. I'll definitely do some videos on them as well, particularly rtt.emask, which is pretty powerful and a little bit more complex. But what I'm really going to do today is just talk about how these objects as a category work. All right. So I'm going to open up a new patch for you here. And we'll just use RTT Euclidean as our example. And I'm going to zoom in a little bit here. So off the bat, you can see we have 3 inlets and 4 outlets. I'm going to set some attributes so that I can actually generate a pattern. And the pattern that I create is always going to come out of the right outlet. So if I manipulate some of these parameters, you can see that I'm actually getting the pattern pre-appended by this symbol pattern. And you can visualize that pattern using this abstraction called rtt.extra.stepGridViewer, which is an abstraction. We'll turn that into a B patcher. And then what I'm going to do is connect that 4th outlet to the step-grid viewer. And then as I change the pattern, you can see that it's being visualized on the B patcher. If you're using rtt.pattern, which is the one where you kind of generate the list of zeros and ones, and you want to use this abstraction, you can. All you have to do is take it and click this little pencil icon to put it in editing mode. And then you can actually send the pattern into rtt.pattern. So that's how you do that. And then you can set the length of the pattern like that. But for any of these ones that are generating the pattern, you will usually connect the output of that last outlet to that abstraction. The other thing to connect usually is going to be this 3rd outlet. And this basically outputs a signal that indicates the current position in the pattern. So if I send a number in, actually what I'm going to do is like this. I'm going to create an integer box, and then I'm going to create an ink duck object. And then I'm just going to convert that into a signal. And so I'm going to be sending that as a signal into the object. And you can see that the value that we're getting here from the 3rd outlet is the current position within the pattern. And one thing you'll notice is that as I go from 16 to 17, it's looping back around to the beginning of the pattern. So there's a wrap, or what you might call a modulus, that is built into the pattern objects. So this first inlet that I'm sending this counter signal into is the one where basically its purpose is for us to send in a signal that specifies a particular position in the pattern. And by default, the object is expecting you to give it an index, so some whole number or integer. And then, like I said, it's going to apply that modulus to wrap it around. If you want to pass a phasor in, so say you have rtt.clock, transport state 1, and I'll add a scope here. If you want to use a phasor instead of an indexed signal like this, you can. All you have to do is set the counter attribute of this object to normalized or norm. And so now when I feed in a phasor, you can see that we're using the phasor to advance through the pattern. Most of the time when you use the pattern objects, I find this works, but I find that most of the time you want to use some type of subdivider that's going to perform this indexing of the clock. And you can use a subdiv object, or you could use rtt.loop. So rtt.loop, its second outlet will produce a counter signal. And by default, rtt.loop is going to count using a subdivision of 16, and it's going to create 16 steps. So by increasing the subdivision, I can basically speed up the rate at which we advance through this pattern. Oops, we're still in normalized mode. So now we're going through it really fast. If I wanted to go through it more slowly, I could say 8. So that's what the subdivision does. I can also change the number of steps of the pattern that I actually play by changing the steps parameter of rtt.loop. So if I only wanted to say play the first 9 steps of this pattern, I could do that. You could see that it's now jumping back to the beginning. Another thing that you could do is set a value that's greater than the length and then have it kind of resetting at a certain point. So if I say 22 or something, it's going to go all the way through the entire pattern. And then it will at some point reset. So this is a feature that's really common on like the Electron gear, where you have multiple tracks. You can set the lengths of those tracks independently, but then you also have sort of a pattern level, pattern length that will reset all of the individual counters, which can be very interesting rhythmically and sort of compositionally. So with the rtt.loop, the subdivision determines the sort of speed of the pulse of advance, and this steps is in control of what number you count to, basically. And you can use that in creative ways to control how your patterns get played back. If you know that you always want to play back the whole pattern, what you could always do is just connect the steps attribute for both of these to both. You could control the steps with the same message to both of them. So because they both have an attribute called steps, this will work. So now if I change the length of the pattern, I'm also changing the length of the count. Now, rtt.loop also has a feature called direction, which allows us basically to change the direction in which it advances through the pattern. So I could go backwards if I wanted to. And I could do ping pong, and I can jump around randomly and things like this. And this actually raises an issue, because if I hit the same step twice, then rtt.euclidean or any pattern object doesn't know that I've actually tried to play another step that is the same step. This is important because the other two outlets of the object output signals that correlate to sort of a new event happening. So if I grab this scope here and I just connect it to the second outlet, you can see that we're getting an impulse for each activated step. So each time we land on one of these green steps, and I'm going to go back into forward mode. Each time we land on one of these green ones, we're getting an impulse. If we're in random mode, it's possible for the same step to get sent twice from rtt.loop, but rtt.euclidean doesn't actually know that I'm asking for it to reevaluate the same step. So to solve that type of situation, what we're going to do is change a different mode, which is called trigger, which is off screen. There we go. And we're going to basically say the signal that comes into the first inlet is going to tell the object what step it needs to evaluate. And that could be indexed or normalized the way that I said before. But then we also are going to require that there's additionally an impulse, which we can get from the third outlet of rtt.loop, to go into the second inlet that tells us when to make that evaluation. So if I now go into trigger mode both, in this situation, what this means is it expects you to send it a signal into the first inlet that's going to tell it which step it should evaluate, but it won't do anything. Like if I disconnect this trigger, you can see it's not advancing around. It's not giving us any impulses because all we've told it is, hey, when I send you an impulse, I want you to evaluate this specific step, but it's not going to do anything until I send that impulse. And at that point, it actually does it. So this is actually a little bit similar. If you saw the clock sources video for RTT, there's a thing where I was talking about how you can reset the phase of the clock, and you can send a signal in that kind of, has this value that represents a phase, but you actually need to send an impulse into the object to actually get it to do that. It's kind of a similar situation because signals in Macs are just a constant stream of data, right? They're not events. They're just fire hoses of numbers. We sometimes need a separate event-like type of signal, which is an impulse, to tell it, hey, I'm ready for you to actually look at this given step, tell me whether or not there is an event there, and produce an impulse. So anytime, the rule of thumb is, anytime that you believe that you're going to be creating consecutive steps that have the same step index, then you want to put it in both mode and you want to connect this trigger inlet. If you're not sure, you might as well go ahead and do it because there's no downside to doing things this way. But if you're just, working in, say, forward mode, which is actually what we are right now, and you don't expect to have the same step reoccurring twice, then you can safely just leave it in its default mode and just connect the one patch cord. And the way that this one works is it kind of produces the trigger internally by identifying a change in the value. So if I go from, some value to another value, it goes, hey, I can sort of predict that you are trying to change the step. And so I'm going to just evaluate that new step that you've given me. Along these same lines, if you, for whatever reason, don't have a counter signal available to you, so you don't have an index or a ramp or anything available to you, and you only have a stream of impulses. So let's just take a stream of impulses by itself. And actually, let me put a scope here so that you can see what rtt.loop is producing. So that's just producing an impulse that is correlated to the subdivision attribute, subdiv attribute of rtt.loop. If you had only that, and you wanted the pattern to just advance in the forward direction each time it received an impulse, then you want to set this trigger attribute to trigger. And what that will do is, every time it gets an impulse, it's going to increment a counter that lives inside of the object. So, I find for most cases that setting things up in the traditional way where you are merely patching a counter signal, so the second outlet of rtt.loop or the second outlet of subdiv, into the first inlet of rtt.euclidean, and then not worrying about either of these parameters, counter or trigger, works great. But if you have something else going on, you have different types of signals that you're working with, or you're sending in random values, or you're sending in indexes that might repeat, then you might need to configure some things in order to make this work. So let me put things back into the normal setup. So counter, and then just sending that counter signal from rtt.loop. So as I've shown you, moving kind of from right to left, the object produces first a pattern, then a step in ID, which is really mainly useful for visualization, then a stream of impulses, and then finally from the first outlet, it also produces some type of counter, although it's different from what the third outlet is producing. And this is another one where an attribute of the object kind of controls what happens here. And that attribute is called output. So in the normal state, the output is called event count, which basically means that every time we have an activated step, or in other words, every time we have an impulse, we're just going to add to an internal counter. So you can see here that this value is actually quite big because this is the number of events that have happened since this video started, basically, since this patch started running. I can update this counter or reset this counter by sending an impulse into the third inlet and have it go back to the beginning. Or I can change what it outputs. So I could get it to produce, instead of this kind of ever-increasing event count, I could have it output nothing. I could have it just echo the input back out. So the value that I'm getting, counter value that I'm getting from rtt.loop is just getting passed on through, except in cases where the step is not activated, by the way, right? Anytime the step is not active, it's just going to send 0. I could also get it to output the same thing as the third outlet, except, again, inactive steps are 0. I could have it output the event index. So this is basically, if we were to count 1, 2, 3, 4, 5 for just those green notes, that's what that is. And then finally is gate, where we'll just get a 1 for activated steps and a 0 for inactive steps. So it's a little bit like the impulse, but we actually get a gate signal that persists for the length of the step. So you have lots of flexibility here, and it really depends on what it is that you're trying to do downstream that will determine which of these you use. I find that most often when I'm working with this, I'm using either event count, which is the default, that's by far the most common one that I use, or I'll use gate, because I might be using rtt.euclidean to open or close a gate, right? Cause or prevent something from happening. So the 0 and 1 can be used in that type of scenario. But most of the time I'm using the event count. And the reason is that I might have an object like rtt.notes, which is basically a container for MIDI note values. So I'm going to create a multi-slider here. Its size is going to be 8, so 8 sliders. And then the minimum and maximum values are going to be 0 and 1. And rtt.notes, I think I talked a little bit about in the video where I made the simple sequencer, and I'll do another one on this, but basically it takes a normalized list. So it takes a list of values from 0 to 1, and then it kind of turns those into MIDI. And there's some settings that control that. I won't get into it, but basically we're doing the same thing here where we're advancing through this little melody that I've drawn in the multi-slider. And just like the pattern objects, there's a modulus built in. So even though I'm sending a number that's like 450, the rtt.notes object is smart enough to just wrap around internally within that sequence. And we're always just going to get that sequence looping if we pass this particular input in. This is where you can actually start to get kind of creative with how your sequencers work. And one of the things that I was excited about doing when I developed RTT was the idea of being able to kind of decouple these different stages from one another, right? So the idea of having a clock and a kind of step counter, and then separately having a pattern generator, and then separately having a melody generator, and also velocities and other things, to have those all independent from one another and have lots of control and flexibility in terms of actually how we send the counters into those objects. We can play back the patterns in really interesting ways. For example, I could have a second rtt.loop here, which could be in random direction. And I know my patch is really messy. I'll delete some stuff here that we don't need. So this is running in random direction. I could set my rtt.euclidean, let's say, to the oops, sorry. Yeah, zoom out a little bit. The gate mode, and then I could just multiply that by the random direction that we get. Oops, wrong outlet here of rtt.loop. And so now what we're actually doing is reading in a kind of random order from this list of notes. So we're kind of reading the melody back in a random order, but the pattern is being read back in the forward direction because it's being controlled by a separate rtt.loop. So there's a lot of flexibility that you have there in order to kind of make the sequencer do weird things and add variation and excitement into your patterns. Oh, shouldn't be doing that. There we go. So now we're saying if this step is activated, then pass through the randomly generated value from the rtt.loop. If the step is not activated, then just multiply by 0, so we'll get 0. Very often I find that you will want to use both the counter and the impulse that the pattern modules create. And a really classic example is if you're going to send MIDI. So if I use rtt.makeNote, which basically takes in signals and turns them into MIDI messages. So if I have a MIDI out and I simply connect this here, and I patch the note value into the first inlet, because that's where that goes, to actually tell rtt.makeNote to generate a MIDI note, right? To like generate a node on event. We can actually monitor what the object is going to produce by just throwing a MIDI parse in here. We need to send an impulse. So I'll take that second outlet of rtt.euclidean and patch it into the final inlet of rtt.makeNote. So, and now we're actually generating those MIDI notes. And that can be true if, you know, you're triggering an envelope inside of Max or a synth or whatever it is that you're doing. Very often I've been finding that it's useful to have sort of pitch and velocity and these kinds of things, but then have an impulse that actually signifies the beginning of a given event. I think that's basically all I have to say about the pattern objects. There's a lot of really cool ways in which these can be used that's not totally obvious. The most classic one is kind of what we're doing here, where we have a clock that goes into a counter like rtt.loop, and then we're generating a rhythmic pattern. But I'd encourage you to think about other exciting ways in which these can be used. One is the Euclidean accents type of example, like I showed in another video recently. Another one is having multiple patterns that kind of interact with one another. So there's another object called rtt.rlogic, which allows you to use Boolean logic to compare signals. So you could have two pattern generators that are generating different patterns, and then have a comparison of those two patterns actually be the result, the rhythmic result that you're producing. You can also do things like say you had a really rapid pulse of events, say from something like the bouncing ball rhythms. There was a video on that a really long time ago, and you're getting this kind of repeated pulse. If you pass that into the trigger inlet and use the trigger mode, so that would be trigger. Maybe not the best naming, by the way, but hopefully you get it. That can be a way to kind of gate or like ignore certain events, so you can actually kind of affect rhythms themselves. And you could even have chains of pattern generators that manipulate rhythms in different ways. So there's a lot that you can do there. I'm curious to hear what you think about some of the applications of these are. If you have any cool ideas, would love to hear them in the comments down below. We also have some folks in the Discord channel talking about this stuff. So if you're interested, if you have questions, if you just want to chat with other nerds, you're super welcome in the Discord. So please join. The link is down below. I think that's it. I'll see you next time. Thanks.